So here we begin the start of Chapter 7. And as we get into Chapter 7, we're going to come back to something we had left off of several chapters ago. And what we're really going to focus on in Chapter 7 are the electrons. Why the electrons? Well, quite simply, it's the electrons that control all of bonding. And so while the protons are important, they determine what element we have. The neutrons have their importance as well. Different isotopes have many, many different purposes. But what we're most concerned with is bonding. Bonds forming, bonds breaking. And everything that we deal with when it comes to bonding is controlled by the electrons. Now, what complicates this further is the fact that once we get down to the atomic level, the physics that we're used to, what we commonly refer to as Newtonian physics, physics that we can see, physics for everyday objects, it doesn't work anymore. And it wasn't until the early, late 1800s, very late 1800s, but more the early 1900s, that the area of quantum mechanics began to develop. And quantum mechanics is something that, to us in the sort of the macro world where we can see things, quantum mechanics ends up being irrelevant. But at the atomic level, quantum mechanics has a lot of very, very significant consequences. And while in this class we're only going to touch on some of the basics, it's a fascinating and somewhat mind-warping topic that really deserves its own couple of weeks to talk about. Unfortunately, we don't have time for that in this course, but I would like to refer to, if you are interested, the following person has written a number of books on quantum mechanics that deal with various aspects of quantum mechanics, as well as other topics. But he does a very, very good job of explaining these topics.
My new book, The Hidden Reality, takes on a grand question. Is our universe the only universe? You see, there's a growing belief among scientists like me that ours may only be one among many universes populating a gigantic cosmos. In The Hidden Reality, I explore this possibility without presuming any knowledge of mathematics or physics on the part of the reader.
Hysterical.
Now,
I'm glad you talked me into this. We work so hard, sometimes it's nice to goof off and do something silly.
Agreed. Wait till you hear how he dumbs down Werner Heisenberg for the crowd. You may actually believe you're in a comedy club.
you can think about Heisenberg's uncertainty principle much like the special order menu that you find in certain Chinese restaurant where you have dishes in column A and other dishes in column B. And if you order the first dish in column A, you can't order the corresponding dish in column B. That's sort of like the uncertainty principle.
Bump.
Say, I heard an interesting tidbit about Howard and Bernadette.
Really, Amy? Gossip? I'm disappointed in you.
Now. Evolutionary biologist Robin Dunbar has identified...
So the person you saw in this clip is Brian Greene, and he's written a number of books getting into quantum mechanics, as well as cosmology that are meant for a non-scientific audience. So if you want to learn more about these, some of his books are an absolutely terrific place to start. But what's going on at the atomic level that makes things so different? Well, first we want to talk about what waves are. So a wave we can define in the following way. So if here's a line, and we'll draw our wave in here in red. And the waves continue like that, sort of indefinitely. And we can label a couple of key points. The bottom is what we call the trough, and the peak is up at the top. Then we have what's known as the amplitude. That's the difference in height between the sort of the midpoint and the peak. And then probably the most important item that we deal with when it comes to waves is here. So you can see between these two gray lines, we've undergone one complete cycle of the wave. And so we can measure the distance here, and that's known as the wavelength. And the wavelength determines what the light is. So wavelength can go anywhere from picometers all the way up to kilometers. When we're dealing with these very, very small ones like picometers, we're talking about things such as gamma rays and X-rays. And very, very long wavelength waves up in the kilometer range, these are most often associated with radio waves. So the wavelength determines what the type of light is, or what it is, what type of wave. The amplitude, how tall the wave is, determines the intensity. The other item we need to define is the frequency. The frequency is the number of peaks that pass through a point in a given time. Usually this is 1 second. And so the units for this are either inverse seconds or hertz. Now, you might expect here, and it probably wouldn't be surprising, that if wavelength is the distance from peak to peak, or distance between 2 points on a wave, and that frequency is the number of peaks that can pass through a point in a given time, that there's probably a relationship between frequency and wavelength. And that's what we find. C is equal to lambda nu, where C is 3 times 10 to the 8 meters per second. This is the speed of light. Lambda is the wavelength, and that wavelength is generally going to be in meters. And nu here is the frequency in inverse seconds. So in other words, the longer the wavelength, the lower its frequency. The shorter the wavelength, the more peaks it can pass through a point in a given time. So the shorter the wavelength, the higher the frequency. So in other words, frequency and wavelength are inversely proportional to each other. But it ended up going a step further. And so later on, de Broglie sorry, that's not de Broglie. But it turns out we can actually relate the energy of any object to its wavelength, as E is equal to hc over lambda. C, again, is the speed of light, lambda is the wavelength, and h is known as Planck's constant, and has a value of 6.626 times 10 to the minus 34th joules times seconds. And Planck's constant is named after Max Planck, who was one of the founders of quantum theory. So de Broglie came along. We're not going to look at his equations, but de Broglie claimed then and showed that we could think literally of any object as a wave. And there ends up being an equation that you can use to calculate that. We're not going to worry about that in this class. But if you know the mass and the velocity, you can calculate the wavelength for any object. Now, in general, this doesn't affect us. You can calculate the wavelength for your car driving down the highway, or you walking walking around. But those, because of the way it's calculated, the wavelengths end up being such small values that they really don't matter. But when they do matter is when you start dealing with light and with electrons. And so it turns out that with both light and electrons, they end up showing properties of both waves and particles. So we go a few years later, and we're still in the early 1900s, to Heisenberg, who developed what's known as the Heisenberg uncertainty principle. Now, I'll show you the equation for it. This is not an equation you're going to need to know. But Heisenberg said that delta x times delta p has to be greater than or equal to h over 4 pi. Now, what are each of these terms? So delta x is the uncertainty in position. Delta p is the uncertainty in an object's momentum. So in other words, what we're saying is for any object, no matter how well we think we know where it is, there's going to be some uncertainty in where it is. Same thing with its momentum, how quickly it's moving. There's always going to be some uncertainty. And that the product of those uncertainties has to be greater than Planck's constant divided by 4 pi. Now again, for most objects, it doesn't matter. If we start plugging in values that would describe, the position of the building you're in right now, maybe it has an uncertainty of 10 to the minus 30th, minus 32nd. We're definitely not going to notice that kind of different uncertainty in where it is or how it's moving. So why does this matter? Well, it matters when we're dealing with electrons. For an electron, this delta X can be the size of the entire atom. So does that mean that we don't know exactly where the electrons are within an atom? And the answer, remarkably, is yes. In fact, one of the interesting things about electrons is, let's say we were trying to determine their position. Well, because of how small electrons are, the mere act of observing the electron ends up changing its momentum. Whereas if we try to accurately determine its momentum, that's going to change where the electron is. Just the mere act of measuring it has an effect on it, and because the electron is so small and so light, again, just the idea of observing it can change where it is or how it's moving. So once Heisenberg did this, we left off in chapter 2 with the Bohr model of the atom. So let's see if we can bring that in here. All right, that picture doesn't seem to want to load. So remember, the Bohr model is where we have our nucleus, and then the electrons operate in these orbits around the nucleus. So how is it that Heisenberg was able to disprove the Bohr model? Well, if these electrons are in well-defined orbits, then that means they're following a well-behaved, well-defined path. And that means there wouldn't be any uncertainty in their position. And that would mean that we could accurately determine both their position as well as their momentum. So in our next video, we will continue with, well, where do we go from here?